digital subscriber line is a family of technologies that provide Internet access by transmitting digital data using a local telephone network which uses the public switched telephone network. In telecommunications marketing, the term DSL is widely understood to mean asymmetric digital subscriber line, the most commonly installed DSL technology. DSL service is delivered simultaneously with wired telephone service on the same telephone line. This is possible because DSL uses higher frequency bands for data. On the customer premises, a DSL filter on each non-DSL outlet blocks any high-frequency interference, to enable simultaneous use of the voice and DSL services. The bit rate of consumer DSL services typically ranges from 256 kbits to over 100 Mbits in the direction to the customer, depending on DSL technology, line conditions, and service level implementation. Bit rates of 1 Gbps have been reached in trials. In ADSL, the data throughput in the upstream direction is lower, hence the designation of asymmetric service. In symmetric digital subscriber line services, the downstream and upstream data rates are equal. Researchers at Bell Labs have reached broadband speeds of 10 Gbps, while delivering 1 Gbps symmetrical ultra-broadband access services using traditional copper telephone lines. These speeds can be achieved with existing telephone lines and can be used to deliver broadband where fiber optic cables can't be installed to the premise. A 2007 book described DSL as the most globally prolific broadband access technology, yet it is only available to around 75% of the population in many developed countries. A 2012 survey found that DSL continues to be the dominant technology for broadband access with 364.1 million subscribers worldwide. History: the theoretical foundations of DSL, like many other forms of communication technology, can be traced back to Claude Shannon's seminal 1948 paper, A Mathematical Theory of Communication. An early patent was filed in 1979 for the use of existing telephone wires for both telephones and data terminals that were connected to a remote computer via a digital data carrier system. The motivation for digital subscriber line technology was the Integrated Services Digital Network specification proposed in 1984 by the CCITT as part of Recommendation I-120, later reused as ISDN digital subscriber line. Employees at Bellcore developed asymmetric digital subscriber line and filed a patent in 1988, by placing wideband digital signals above the existing baseband analog voice signal carried between telephone company telephone exchanges and customers on conventional twisted pair cabling facilities. Consumer-oriented ADSL was designed to operate on existing lines already conditioned for basic rate interface ISDN services, which itself is a digital circuit switching service, though most incumbent local exchange carriers provision rate-adaptive digital subscriber line to work on virtually any available copper pair facility whether conditioned for BRI or not. Engineers developed higher-speed DSL facilities such as high bit-rate digital subscriber line and symmetric digital subscriber line to provision traditional digital signal one services over standard copper pair facilities. A DSL circuit provides digital service. The underlying technology of transport across DSL facilities uses high-frequency sinusoidal carrier wave modulation, which is an analog signal transmission. A DSL circuit terminates at each end in a modem which modulates patterns of bits into certain high-frequency impulses for transmission to the opposing modem. Signals received from the far-end modem are demodulated to yield a corresponding bit pattern that the modem retransmits, in digital form, to its interfaced equipment, such as a computer, router, switch, etc. Unlike traditional dial-up modems, which modulate bits into signals in the 300–3400 Hz baseband, DSL modems modulate frequencies from 4000 Hz to as high as 4 MHz. This frequency band separation enables DSL service and plain old telephone service to coexist on the same copper pair facility. Generally, higher bit rate transmissions require a wider frequency band, though the ratio of bit rate to symbol rate and thus to bandwidth are not linear due to significant innovations in digital signal processing and digital modulation methods. Early DSL service required a dedicated dry loop, but when the U.S. Federal Communications Commission required ILECs to lease their lines to competing DSL service providers, shared Line Dsl became available. Also known as DSL over Unbundled Network Element, this unbundling of services allows a single subscriber to receive two separate services from two separate providers on one cable pair. The DSL service provider's equipment is co-located in the same central office as that of the ILEC supplying the customer's pre-existing voice service. The subscriber's circuit is then rewired to interface with hardware supplied by the ILEC, which combines a DSL frequency and POTS frequency on a single copper pair facility. On the subscriber's end of the circuit, Inline low-pass DSL filters are installed on each telephone to filter the high-frequency hiss that would otherwise be heard, but pass voice frequencies. Conversely, high-pass filters already incorporated in the circuitry of DSL modems filter out voice frequencies. Although ADSL and RADSL modulations do not use the voice frequency band, nonlinear elements in the phone could otherwise generate audible intermodulation and may impair the operation of the data modem in the absence of low-pass filters. Older ADSL standards delivered 8 Mbps to the customer over about 2 km of unshielded twisted pair copper wire. Newer variants improved these rates. Distances greater than 2 km significantly reduce the bandwidth usable on the wires, thus reducing the data rate. But ADSL loop extenders increase these distances by repeating the signal, allowing the LEC to deliver DSL speeds to any distance. By 2012, some carriers in the United States reported that increasing use of fiber optics was leading to steadily declining numbers of DSL users. Operation: basic technology. Telephones are connected to the telephone exchange via a local loop, which is a physical pair of wires. Prior to the digital age, the use of the local loop for anything other than the transmission of speech, encompassing an audio frequency range of 300 to 3400 Hz, was not considered. However, as long-distance trunks were gradually converted from analog to digital operation, the idea of being able to pass data through the local loop took hold, ultimately leading to DSL. For a long time it was thought that it was not possible to operate a conventional phone line beyond low speed limits. In the 1950s, ordinary twisted pair telephone cable often carried 4 MHz television signals between studios, suggesting that such lines would allow transmitting many megabits per second. One such circuit in the UK ran some 10 miles between the BBC studios in Newcastle upon Tyne and the Pontop Pike transmitting station. It was able to give the studios a low-quality Q feed but not one suitable for transmission. However, these cables had other impairments besides Gaussian noise, preventing such rates from becoming practical in the field. The 1980s saw the development of techniques for broadband communications that allowed the limit to be greatly extended. The local loop connecting the telephone exchange to most subscribers has the capability of carrying frequencies well beyond the 3.4 kHz upper limit of POTS. Depending on the length and quality of the loop, the upper limit can be tens of megahertz. DSL takes advantage of this unused bandwidth of the local loop by creating 4,312.5 Hz wide channels starting between 10 and 100 kHz, depending on how the system is configured. Allocation of channels continues at higher and higher frequencies until new channels are deemed unusable. Each channel is evaluated for usability in much the same way an analog modem would on a POTS connection. More usable channels equates to more available bandwidth, which is why distance and line quality are a factor. The pool of usable channels is then split into two different frequency bands for upstream and downstream traffic, based on a pre-configured ratio. This segregation reduces interference. Once the channel groups have been established, the individual channels are bonded into a pair of virtual circuits, one in each direction. Like analog modems, DSL transceivers constantly monitor the quality of each channel and will add or remove them from service depending on whether they are usable. Joseph W. Leclider's contribution to DSL was his insight that an asymmetric arrangement offered more than double the bandwidth capacity of symmetric DSL. This allowed Internet service providers to offer efficient service to consumers, who benefited greatly from the ability to download large amounts of data but rarely needed to upload comparable amounts. ADSL supports two modes of transport, fast channel and interleaved channel. Fast channel is preferred for streaming multimedia, where an occasional dropped bit is acceptable, but lags are less so. Interleaved channel works better for file transfers, where the delivered data must be error-free but latency incurred by the retransmission of error-containing packets is acceptable. Because DSL operates above the 3.4 kHz voice limit, it cannot pass through a load coil. Load coils are, in essence, filters that block out any non-voice frequency. They are commonly set at regular intervals in lines placed only for POTS service. A DSL signal cannot pass through a properly installed and working load coil, while voice service cannot be maintained past a certain distance without such coils. Therefore, some areas that are within range for DSL service are disqualified from eligibility because of load coil placement. Because of this, phone companies endeavor to remove load coils on copper loops that can operate without them, and by conditioning other lines to avoid them through the use of fiber to the neighborhood or node. The commercial success of DSL and similar technologies largely reflects the advances made in electronics over the decades that have increased performance and reduced costs even while digging trenches in the ground for new cables remains expensive. Several factors contributed to the popularity of DSL technology. Until the late 1990s, the cost of digital signal processors for DSL was prohibitive. All types of DSL employ highly complex digital signal processing algorithms to overcome the inherent limitations of the existing twisted pair wires. Due to the advancements of very large-scale integration technology, the cost of the equipment associated with a DSL deployment lowered significantly. The two main pieces of equipment are a digital subscriber line access multiplexer at one end and a DSL modem at the other end. A DSL connection can be deployed over existing cable. Such deployment, even including equipment, is much cheaper than installing a new, high-bandwidth fiber optic cable over the same route and distance. This is true both for ADSL and SDSL variations. In the case of ADSL, competition in Internet access caused subscription fees to drop significantly over the years, thus making ADSL more economical than dial-up access. Telephone companies were pressured into moving to ADSL largely due to competition from cable companies, which used DOCSIS cable modem technology to achieve similar speeds. Demand for high-bandwidth applications, such as video and file sharing, also contributed to popularize ADSL technology. Most residential and small office DSL implementations reserve low frequencies for POTS service, so that the existing voice service continues to operate independent of the DSL service. Thus POTS-based communications, including fax machines and analog modems, can share the wires with DSL. Only one DSL modem can use the subscriber line at a time. The standard way to let multiple computers share a DSL connection uses a router that establishes a connection between the DSL modem and a local Ethernet, power line, or Wi-Fi network on the customer's premises. Once upstream and downstream channels are established, a subscriber can connect to a service such as an Internet service provider. Naked DSL. A naked DSL is a way of providing DSL services without a PSTN service. It is useful when the customer does not need the traditional telephony voice service because voice service is received either on top of the DSL services or through another network. It is also commonly called a UNE for unbundled network element in the USA and known as a ULL service in Australia. It started making a comeback in the US in 2004 when Quest started offering it, closely followed by Speakeasy. As a result of AT&T's merger with SBC, and Verizon's merger with MCI, those telephone companies have an obligation to offer naked DSL to consumers. Even without the regulatory mandate, however, many ILECs offer naked DSL to consumers. The number of telephone landlines in the U.S. dropped from 188 million in 2000 to 115 million in 2010, while the number of cellular subscribers has grown to 277 million. This lack of demand for landline voice service has resulted in the expansion of naked DSL availability. Naked DSL products are also marketed in some other countries, for example Australia, New Zealand and Canada. Typical setup: on the customer side, the DSL transceiver, or ATUR, or more commonly known as a DSL modem, is hooked up to a phone line. The telephone company connects the other end of the line to a DSL AM, which concentrates a large number of individual DSL connections into a single box. The location of the DSL AM depends on the telco, but it cannot be located too far from the user because of attenuation between the DSL AM and the user's DSL modem. It is common for a few residential blocks to be connected to one DSL AM. When the DSL modem powers up, it goes through a sync procedure. The actual process varies from modem to modem but generally involves the following steps. The DSL transceiver performs a self-test. The DSL transceiver checks the connection between the DSL transceiver and the computer. For residential variations of DSL, this is usually the Ethernet port or a USB port. In rare models, a Firewire port is used. Older DSL modems sported a native ATM interface. Also, some variations of DSL use synchronous serial connections. The DSL transceiver then attempts to synchronize with the DSL AM. Data can only come into the computer when the DSL AM and the modem are synchronized. The synchronization process is relatively quick but is very complex, involving extensive tests that allow both sides of the connection to optimize the performance according to the characteristics of the line in use. External, or standalone modem units have an indicator labeled CD, DSL, or link, which can be used to tell if the modem is synchronized. During synchronization the light flashes. When synchronized, the light stays lit, usually with a green color. Modern DSL gateways have more functionality and usually go through an initialization procedure very similar to a PC boot up. The system image is loaded from the flash memory. The system boots, synchronizes the DSL connection and establishes the IP connection between the local network and the service provider, using protocols such as DHCP or PPPoE. The system image can usually be updated to correct bugs, or to add new functionality. The accompanying figure is a schematic of a simple DSL connection. The right side shows a DSL AM residing in the telephone company's central office. The left side showed the customer premises equipment with an optional router. This router manages a local area network of which are connected some number of PCs. With many service providers, the customer may opt for a modem which contains a wireless router. This option often simplifies the connection. Exchange equipment: at the exchange, a digital subscriber line access multiplexer terminates the DSL circuits and aggregates them, where they are handed off to other networking transports. In the case of ADSL, the voice component is also separated at this step either by a filter integrated in the DSL AM or by a specialized filtering equipment installed before it. The DSL AM terminates all connections and recovers the original digital information. Customer equipment: the customer end of the connection consists of a terminal adapter or DSL modem. This converts data between the digital signals used by computers and the voltage signal of a suitable frequency range which is then applied to the phone line. In some DSL variations, the terminal adapter connects directly to the computer via a serial interface, using protocols such as Ethernet or V35. In other cases, it is common for the customer equipment to be integrated with higher-level functionality, such as routing, firewalling, or other application-specific hardware and software. In this case, the equipment is referred to as a gateway. Most DSL technologies require installation of appropriate filters to separate, or split, the DSL signal from the low-frequency voice signal. The separation can take place either at the demarcation point, or with filters installed at the telephone outlets inside the customer premises. Either way has its practical and economical limitations. Protocols and configurations. Many DSL technologies implement an asynchronous transfer mode layer over the low-level bitstream layer to enable the adaptation of a number of different technologies over the same link. DSL implementations may create bridged or routed networks. In a bridged configuration, the group of subscriber computers effectively connect into a single subnet. The earliest implementations used DHCP to provide network details such as the IP address to the subscriber equipment, with authentication via MAC address or an assigned host name. Later implementations often use point-to-point protocol or asynchronous transfer mode or point-to-point protocol over ATM, while authenticating with a user ID and password and using point-to-point protocol mechanisms to provide network details. Transmission methods. Transmission methods vary by market, region, carrier, and equipment. 2B1Q, 2 binary, 1 quaternary, used for IDSL and HDSL, CAP, carrierless amplitude phase modulation, deprecated in 1996 for ADSL, used for HDSL, TCPAM, trellis-coded pulse amplitude modulation, used for HDSL2 and SHDSL, DMT. Discrete multi-tone modulation, the most common kind, also known as OFDM, DSL technologies. The line length limitations from telephone exchange to subscriber impose more restrictions on higher data transmission rates. Technologies such as VDSL provide very high-speed, short-range links as a method of delivering triple-play services. Technologies like GDSL can further increase the data rate of DSL. Fiber optic technologies exist today that allow the conversion of copper-based ISDN, ADSL and DSL over fiber optics. DSL technologies include symmetric digital subscriber line, umbrella term for XDSL where the bitrate is equal in both directions. ISDN digital subscriber line, ISDN-based technology that provides a bitrate equivalent to 2 ISDN bearer and 1 data channel, 144 kbits symmetric over 1 pair, high bitrate digital subscriber line, ITU-TG 991.1, the first DSL technology that used a higher frequency spectrum than ISDN, 1544 kbits and 2048 kbits symmetric services either on 2 or 3 pairs at 784 kbits each, 2 pairs at 1168 kbits search, or 1 pair at 2320 kbits, high bitrate digital subscriber line 2 quarters, ANSI, 1544 kbits symmetric over 1 pair or 2 pairs, symmetric digital subscriber line, specific proprietary technology, up to 1544 kbits symmetric over 1 pair, single pair high-speed digital subscriber line, ITU-TG 991.2, standardized successor of HDSL and proprietary SDSL, up to 5696 kbits per pair, up to 4 pairs. Asymmetric digital subscriber line, umbrella term for XDSL where the bitrate is greater in one direction than the other. ANSIT 1.413 SU2, up to 8 Mbit/s and 1 Mbit/s, GDMT. ITU-TG 992.1, up to 10 Mbit/s and 1 Mbit/s, G-Lite, ITU-TG 992.2, more noise and attenuation resistant than GDMT, up to 1536 kbits and 512 kbits, asymmetric digital subscriber line 2, ITU-TG 992.3, up to 12 Mbit/s and 3.5 Mbit/s, asymmetric digital subscriber line 2 plus, ITU-TG 992.5, up to 24 Mbit/s and 3.5 Mbit/s, very high bitrate digital subscriber line, ITU-TG 993.1, up to 52 Mbit/s and 16 Mbit/s, very high bitrate digital subscriber line 2, ITU-TG 993.2, an improved version of VDSL. Compatible with ADSL2+, some of both directions up to 200 Mbit/s. G-vector crosstalk cancelling feature can be used to increase range at a given bitrate, for example 100 Mbps at up to 500 meters. G-Fast, ITU-T G9700 and G9701, up to approximately 1 Gbps aggregate uplink and downlink at 100 m. Expected to be finalized in April 2014. Bonded DSL rings, a shared ring topology at 400 Mbps, Etherloop Ethernet local loop, high-speed voice and data link, Internet Protocol subscriber line, developed by RIM Semiconductor in 2007, allowed for 40 Mbps using 26 AWG copper telephone wire at a 5,500 AFT radius, 26 Mbps at a 6,000 AFT radius. The company operated until 2008. Rate Adaptive Digital Subscriber Line, designed to increase range and noise tolerance by sacrificing upstream speed, Uni-DSL, technology developed by Texas Instruments, backwards compatible with all DMT standards. See also, John Chufi, known as the father of DSL, broadband Internet access, list of countries by number of Internet subscriptions, dynamic spectrum management, electronic filter, list of device bandwidths, ADSL loop extender, references. Further reading, Dave Burstein. DSL. John Wiley & Sons. ISBN A0-471-08390-9 pages 53 Digital Subscriber Line. International Engineering Consortium 2001. ISBN A978-0-933217-95-9 GSUP 50, Overview of Digital Subscriber Line Recommendations. ITU-T. September 2011. Retrieved December 26, 2013. External links, ADSL Theory Information about the background and workings of ADSL, and the factors involved in achieving a good sync between your modem and the DSL AM.